well-known guest from natural language processing. She's coming from the University of Houston, but precisely from the Mohammed bin Zayed University of Artificial Intelligence. First university in the world about artificial intelligence. It's very nice to have a visit from Professor Thamar and Jingjing. All right. Professor Thamar is a tenured professor of computer science at the University of Houston. She's the director and founder of Ritual Lab. She does a lot of things on natural language processing. I think people know about her work. Many people know that she was the chair of the conference where the Berkeley was awarded a prize. So it's very nice to have her visit, and she'll be talking about her technical work, but also at the life at Mohammed bin Zayed University and opportunities for cooperation visits. So it's very nice to have you. The floor is yours. Thank you.
Thank you so much.
Oh, thank you.
I have this one, yeah. Thank you for the very nice introduction, and thank you so much for welcoming us here. I know you're in the break, and so I understand why it's hard to be here. So I appreciate that you guys came and that you give us this chance to talk. So yes, I'm at Mohammed bin Zayed University. I joined 6 months ago, so I'm on leave from the University of Houston. I still have my position there, but like I asked for permission from some numbers. Saudi Arabia, I think, is number 1. And here on this side, you can see Abu Dhabi. This is where the university is located. It's right across the Zain International Airport in Abu Dhabi, so it's a very convenient location. This is where I live. It's Abu Dhabi is a set of islands, and so you get to choose whether you want to be like me, close to the beach and have a 30-minute commute. Jingjing also lives on that area, so we are very privileged to have access to some of the few natural beaches. Some of the other beaches are man-made, and so you don't have the same experience that we do. I get to see dolphins, for example. Like very often you see dolphins swimming by the shore. This is very unique and very privileged, and I love it. Besides that, I also want to talk a little bit about the university. So the name stands for Mohammed bin Zayed, University of Artificial Intelligence. Mohammed bin Zayed is the king of Abu Dhabi, is the president of the country, and so he's the one that the university bears the name because he's behind this university, right? It's a government-funded university, so the money comes out of the government. But it's a rich country, as you know. I don't know if I should point somewhere else. There you go. So here's a little bit of the university in terms of numbers. I want to give you like an overview. It's not that numbers are everything or the whole picture, but it gives you a little bit of what this university is about. First of all, these are pictures of the campus. This is how the university looks like. These orange buildings are university residences for the students. This is where students' housing is located. This is the knowledge center. This is like where the president and the higher-ups sit, and we have occasional meetings in there. And these are our buildings. These are the rest of the university. So the university was established in 2021, and by now we have 5 departments. We have computer vision, machine learning, NLP, and the latest additions are computer science and robotics. There are other departments in the works, like they're working on expanding. But the main focus is AI, and like I mentioned at the beginning, is the first university in the world that is focused on artificial intelligence. So that's pretty unique. I mean, at the University of Houston, I am the only NLP person, so I had to teach the NLP courses and do all the NLP related. I don't have colleagues to talk to, but here at MBZ, I have an entire department of people that do NLP. Right now, we are 10 plus full-time people, and we have like 5 or 6 part-time people. And we're planning on expanding our faculty up to 20 lines of full-time NLP people for this coming year, maybe more. Although the other departments are also in the same setup of expanding, we're like growing. It's been since 2021, but we still want to continue growing. It's a very cool setting where our president is a machine learning guy. So I don't have to explain to my president what I do as opposed to the University of Houston, because he's a machine learning person. He knows what we do. He knows how we do research. And that's pretty cool. Like, we got a lot of support that understands our research. And so here's the numbers again. So the 5 departments, we have a supercomputing center, we have 3 centers. We are 64 faculty across those departments, at least last time we counted, because every time we keep growing, we're interviewing and we keep growing. We have 276 students. It's a research-only institution, so we only have master's and PhD students. And we have 202 researchers that are part of the ecosystem, and these include research assistants that come for a few months to work with us, as well as postdocs are counted towards this number. There's another, not other numbers, but I think, what's really outstanding is that it's, these statistics are for 3 years ago, and right now we are currently ranked number 18, according to CS rankings across the entire world on AI-related fields. And if you look at, for example, NLP specific, we're worldwide ranked number 18. Machine learning, computer vision as well. I think machine learning we're a little bit 20 or something like that. But it's pretty outstanding. Like they're putting a lot of effort into hiring top talent. Not that I'm tooting my own horn, talking about my colleagues, not myself. Anyhow, so it's a very unique opportunity to work with people. Like I said, I'm very happy to have an entire department that does this, with all of the research, access to researchers and students and the entire environment. The university offers master's and PhD programs fully funded, like you would expect. The students get housing as part of their package. And in addition to that, their stipend goes from $2,500 US for master students to $2,600 US a month for PhD students. So it's very generous. That money is reserved only for the living expenses, because housing and insurance is covered by us. And the university also gives them annual tickets to their home country once a year. So they also pay their flights. So it's a very generous opportunity for people to study. In addition to master's and PhD programs, we have research assistant positions where students enroll in other institutions can come visit us for a few months and work with us. And I think that's the best. It's a very nice way to establish collaborations across different universities and to involve advisors and other institutions, and not just we recruiting students and not collaborating, right? So there's different ways. We have postdoc positions, like I mentioned, also faculty positions. Okay, so that's the university. If you want to hear more, if you have questions, make sure that you contact us, okay? But I also came to talk about our research. Hopefully that is also interesting to you. So let's go back to the research. Today I'm going to talk about language and vision, and in particular the area of question answering. And so we all know, if you're aware of AI, if you're researching either computer vision or machine learning, you probably are aware of the fact that we have made a lot of progress. And now we have available pre-trained models that can do image processing very well. And on the other hand, we also have pre-trained models that we can start using off the shelf that process language very well. And with these advances comes the opportunity that we combine language and vision models to do interesting tasks, right? Which is what eventually we want to accomplish. And so we want to connect modalities, and we want to make sure that the models we develop and use are taking advantage of this language and vision at the same time to do more interesting stuff. So this is what I want to talk about today. We'll be working in this space of vision and language models. And so I'm going to give you today an overview of the previous work, recent work in language and vision multimodal models. And then I'll set up the stage so that I can talk to you about what we have been doing, some recent efforts in this space. And then we can hopefully have Q&A, time for Q&A. Okay, So vision language models for image QA. This is an example of a model, right? It's asking what is in this picture, and the model says it's a ball soup with a monster face on it, and then it's asking what is the monster made out of, and the model says vegetables, and then the user says, no, it's not, it's made out of a specific material, fabric, what is the fabric made out of? So once you involve the information of its fabric, then the model is able to reassess what has interpreted in the image and then fix the interpretation and say, oh, okay, it's made out of wool. And it has, so these models, like it says there, are expected to reason across images and language, pretty much like we do, right? Except that it's pretty hard to accomplish. And capture relationships between visual and linguistic options. So that's the goal. Common architectures for image Q&A include models like PALI, for example, where what they try to do is they have a visual transformer as a base model, and they combine it with a language encoder-decoder model through a fine-tuned process so that the model can reach modalities. So the breaching part here is done by an intensive fine-tuning stage, or training from scratch in this case, which means that it requires a lot of data. The language model that is used as backbone is an MT5, so it allows you, like it shows in the graph, to explore different languages. And the vision model is a trained visual transformer, so they start from a pre-trained visual transformer model to combine. Then on the right-hand side, we have a model like BLEEP2 that is an improvement over the first BLEEP version. This is a very robust model where what they do is they train what they call a Q-former. So they take a frozen image encoder. The frozen image encoder will extract the hidden or an embedded representation of the image that is fed to the Q-former together with the text for that particular image instance. And then the Q-former is expected to learn some mapping that allows to go from the image representation from the encoder into a set of queries that are called. It's a fixed number of embeddings that are extracted from the image, and they're meant to be aligned with the text because this is a transformer model that is trained combined. And then on the other side, they give this to a frozen language model that does the whatever else task you are expected to do, like captioning, describing the image, or doing some answering. And so, but it's still very heavy compute resource wise because you are training this Q-former from scratch. And in order to train this Q-former from scratch, you have to load the image encoder and the language model because this fits into both of them. It's very dense. The underlying visual model is a similar visual transformer, but it's a larger version. So they use either the large or the giant visual transformer. The connection between modalities is done via this Q-former that I mentioned, and the underlying language model is a frozen T5 model, which is an encoder-decoder model based on T5. So here's a little bit more about BLEEP2. I want to go into more details into this because this is one of the models we compare against, or this model builds a foundation for one of the models we compare against state-of-the-art. And so what you see here is that you have the representation learning stage here. They use transformer models to bridge the gap between the modalities. Here is what I mentioned. The Q-former is learning these query representations. We call them feature extractors because they're generating some representation from the image. But as you can see here, it fits into a transformer module where there's information coming from the text as well. And in order for these modalities to be aligned or to enforce better alignment between modalities, the authors use 3 different learning objectives here, or losses or loss terms during the training phase. One of them is image text matching, which has been used a lot before. It was also used during the very well-known CLIP model. So this transformer model is pre-trained to predict whether the representation from the image and the representation from the text belong to the same instance or not. This is this term here. Image and text contrastive learning. Oh, sorry, this is the one that Clip, I think Clip uses this one. Image text contrasting learning. It takes the embedded representation from the text and the one from the image, and it's trying to bring together in the embedded space the representation from the text and the image. They belong to the same instance, while at the same time pulling them apart from text and image representations that are not from the same instance. So this is the idea behind image text contrastive learning. It's a very common learning objective for multimodal models. And then image text element text generation. This is where you are fine-tuning this representation so that the model generates the correct output when you're doing language modeling objective. They have the generative learning stage here, where they pass the output of the Q format that has been pre-trained here through a fully connected layer so that you form a representation that is fed into the frozen language model. And then they train these with the language modeling objective loss. And the idea is that by feeding these representations, the language model is going to generate text that is relevant for the image, or the language generation process is guided by the visual features here. And like I said, it's very intensive. We try to do something like this with the other model I will show you. But you require a large GPU power, and it's super expensive. If you don't have the resources, then this cannot be done. But they try, some of the things they try to make it more manageable is that, oh no, this is another model. I'm talking about a lot of models, so I'm confusing my marbles here. But anyhow, so this is the Bleep 2. We take some ideas from here. The other model I'll mention talks about this. Anyhow, so other common architectures for image question answering are models like Flamingo. Flamingo uses interleaves layers from the visual representation with layers of a pre-trained language model, and they use a gating mechanism. And these are connected via TANH functions so that they can use the weights of a pre-trained language model and connect them to the layers of the visual representation, and they only train, like it says here, they only train the pink part, so the layers that are interleaved with the pre-trained language model. And the frozen language model is a chinchilla model, and the visual encoders are ResNet, a pre-trained ResNet model. Then on the right-hand side, we go from a very different flavor of a model. This Lens paper that was released 2022 tries to change the approach on how we do image question answering by focusing on generating rich textual representations of the image. So instead of wanting to breach modalities or trying to combine modalities during representation learning, for example, they say what we can do better is to try to generate good representations of the image, and then we answer the questions with that text. And so they do, for example, these authors use the CLIP model, and they use prompts like, for example, this is an image of a blank, and the CLIP model needs to fill in the rest. And so if you show, for example, this, you expect that this is an image of a dog on a surfboard, for example, will be an appropriate answer. After that, they also use the CLIP model to generate an attribute vocabulary. So once the model recognizes objects, then those semantic representations of the object classes are fed into the CLIP model to extract attributes of the object. And then they also generate captions. They also give the image and just generate a caption for this image is the prompt. And then they combine all this textual information from the image, and then they feed it to a pre-trained language model, and then the language model does the rest. So if you want to do question answering, the language model does that. So this is a clever idea that it's a gradient-free model. They don't have to tweak any parameters of the models, are frozen, and all the effort is into how can we generate meaningful representations. And so what we do in the paper and the work that I'm going to discuss today is very similar to this, but we're applying it to video. So this is just image. This is a static images. And when you go to video, then there's a whole lot of things that you can do. Okay, so that was images. But what about video, right? Images are a single frame that you extract features and you can do stuff. But when we're talking about video question answering, the problem becomes much more complicated, right? Here's an example of a video where the question is how many objects were put in the backpack throughout the video. So in order for the model to answer that, first of all, the model needs to understand the actions, which actions are resulting in objects being placed in the backpack. It also needs to count, right? And it's not just the fact of how many objects are touched. Like in that case, the glasses are not put into the backpack. So it's a much more complicated type of task. It requires models to reason about what is happening, to keep track of the context. And like I'll show you here, it's much more difficult to do. Common architectures for video Q&A. Frozen BLM is one previous model. What they do is that they extract all the frames and they map the frames into these visual tokens to try to map the visual representations to the textual embedded space. And then they provide all of this prepended to the text. And then they train the whole, well, they train the layers of these models that are interleaved with the frozen pre-trained language model. This is an encoder-only model. This is like your BERT model. So think about it, your BERT model, regular BERT model, but you just add these visual tokens that are generated and fine-tuned during this pre-training stage. So the language is adapted with intermediate models, but it builds on the architecture for BERT. They use all the frames, so when you have videos, you have this decision to make about how many samples I take from the video, right, to extract features. In this case, they take all the frames, they have a sampling rate, and then all the frames that are extracted are fed into this model. Then on the right-hand side, we have Sebila. Sebila is built on the BLEEP2 model that I mentioned at the beginning that I was confusing myself with. And Sebila has two models, a localizer and an answer. It's a complicated solution. It's a huge model because you have these pre-trained language model, this visual pre-trained language model, and in between you're training the Q-former, which is another transformer model. And then you have two phases. The localizer phase, the localizer is called localizer. What it's doing is actually using these queries that are from the BLEEP2 model, but they're using them to select frames. So they're training the Q-former model to say, I'm going to give you a bunch of frames, and then I want you to select frames for me, so that you only focused on the frames that are supposed to be more informative and use those frames to answer the question, okay, instead of using all the frames. And then this is the answerer. Once you have selected your frames, you pass them to the answerer module. You pass them through a linear layer, and then you map them to the embedded space of the text, and you feed them to the language model to answer the question. But these are huge models, right? It uses the visual transformer, the large and the giant, and it tries OPT and FLANTI5. And they use selected keyframes. So here's the model again. This is Sebila. This is the answerer that is trained to provide the answer based on the Q-former, and this is the localizer that is extracting the queries as well as selecting which frames are more relevant. Here's what I was saying before. This model, it's very dense, very complex, because you need to have a huge GPU to load the language model together with the transformer for the Q-former to train. But what they try to do here is that in order to generate in a cheap way supervision signal to train the localizer, once you give this to the FLANTI5 model to answer the question, if the answers for the model are correct, then you take the frames that were selected as these are the right frames, and then you feed them back to the localizer doing more pre-training so that the model gets better at selecting frames. Key issues with this model, we tried it and we see some of the results. It does not consider any temporal information, right? Once you go here, there's no notion of what happened before or what happened next. There's no global reasoning over frames, right? So you do frame selection one by one. You don't do a reasoning over the entire video to select your frames. And what ends up happening is that a lot of the frames are redundant. So the frames end up being selected that are very similar to each other, and they're not helpful. And so there's some of these issues that we have with this. So when we were working with this model, we try a little bit with, we try to do something with the Q-former to do better frame selection, like we do global inference and all. But we found a bottleneck because, like I mentioned, these models are very heavy, very large. So we couldn't fit them into our GPUs. And we said, well, that's a dead end because we cannot go that way. So let's see what else we can do. So we moved in a different direction. We look at instruct bleep. So instruct bleep, like the name says, it builds on bleep, but it's a model that is fine-tuned with instructions. So the Q-former that we saw before, the queries are fine-tuned so that they are relevant to the specific instruction provided to this model. And what they do during pre-training, everything else is the same, is that they pre-train this model with instructions for different tasks. Task could be captioning, task could be describe an object, or task could be, whatever the model is trying to do. But they pre-train this model with 13 different tasks. And what this does is that it makes this model very good at following your instructions because you are fine-tuning the model to understand what you're trying to accomplish with the text. And so we try experiments with this one and with regular bleep too, and this is much better at things that are very fine-grained. Like, for example, when you say to the model, select an answer and give me only one letter out of these options. This model is much better at following those instructions than the previous one, because the previous one will give you, sometimes it will give us longer answers that are not relevant. And then it becomes problematic to evaluate automatically that model. So we use this in our solution. I'll tell you a little bit more about that, but there's one last stop in the set of models that we explore and we have studied is this Lobby model. Lobby came out like November of last year or December of last year. So it's a very recent model. It does, like it says there, long range video question answering. What they do is they use a video clip level captioner. So these are long videos. They take mini clips and then they give them to a multimodal model to generate a caption. It tells me what this clip is about. And then they generate captions for all their clips that they extract. And then they give all those captions, they give them to a pre-trained language model and say, give me a summary of these captions. I give you all the captions and I want you to generate a summary. And generative language models are very good at summarizing, right? That's one of the tasks for which they're very good at. So they generate a summary. Once they have the summary, they give a question answering from the summary and question answering candidates to a GPT 3.5 model to do the answering part. So again, this is similar to the lens in the respect that you're turning everything about a multimodal video question answering task into a language-only task by focusing on extracting good representations that describe the video, and then you answer everything with text. But problem is that they use GPT 3.5, which means they use a closed model that is behind a paywall, and if you want to use that, you have to pay. I have big issues with that. We're doing science. We shouldn't be paying private entities to do research on their models. So that, and on top of that, it's not even reproducible because you have no control when they change what is the back end of the API. You just have an interface with that. So to me, that's not relevant, or that's very hard to reproduce. And again, I have issues with giving them money. But it's a very good model. Here's some examples. You have the question. Why did the boy pick up one person from the group of them and move to the sofa? So these are the little mini clips. And then you can see a little bit of the different captions that are generated for the mini clip. So they sample the model. You can stochastically sample the model to generate different captions for the same input. For example, a room with pink furniture and pink wallpaper, not relevant for the question, but is describing what is happening. A child is standing in a room, a boy is standing in a room with a Christmas tree, a child is standing on a pink couch. But the interesting thing is that once you generate this set of captions that by themselves are not very useful, it appears to the question, once you give them for a summary to GPT 3.5, it gives you nice information about the video that talks about, a present from a group of them, and they move them to the sofa, and what the exact reason is not explicitly described, it can be inferred that the boy is likely drawn to a particular present and decides to bring it to the sofa for further exploration and enjoyment. So like that, that's a very rich explanation that magically GPT 3.5 is able to generate out of the set of captions. So that's pretty cool. But again, it's behind a paywall. We cannot reproduce it. We cannot inspect it. We don't have a way to understand. Even with that, you have common failures with this model. We play with it too. One failure in the captions is or summary leads to wrong answers. So like if your summary doesn't have the answer that or doesn't have the information to provide the answer, there's no way you can recover the answer from. This is one type of error propagation, right? If your captions are not meaningful, or if the summary somehow drops relevant information, it's not going to work. And in the other hand, sometimes even when the summary has enough information, the model is not able to infer the right purpose. So this is asking about why do you have a container with water and needs to clean the paintbrush before you go to a different color. The model just says to provide a source of water for the paintbrush. I mean, yes, if you are very literal, it's providing a source of water for the paintbrush, but the purpose, the meta-level intention of doing that is to clean the paintbrush, right? So that's a lack of reasoning that GPT 3.5 is not able to accomplish. Okay, so I went over a set of state-of-the-art models, recent models, and we look at what they do, how they do bridging from modalities. Some of them are doing heavy training, so end-to-end training to reach modalities. And some others use very large models or models that are closed. And so for our point of view, we want to rely on the abilities of language models by providing more textual information about the videos, similar to the lens idea or the lobby idea, but with open models and smaller models that we can run in our GPU budgets. So this is what we do. We call it QVID for question something video. I'm very bad with names. We just posted this paper on arXiv on Friday, and I forgot to add the link here. But we use captions. The idea is using captions for video QA. Our underlying model, multimodal model, is InstructBleep because, like I mentioned before, in previous studies, we found that this model is really good at understanding instructions. And what we do is we do a captioning prompt. So we ask InstructBleep to generate captions, but we ask the model to give us captions that are relevant for the question. So not just captions. We say, okay, given this image and this question, give me a caption of the image. Not exactly like that, but it says provide a detailed description of the image related to the question X, and we give the question. And so the whole idea is that we want captions, yes, but we want captions that help us answer the question, not just any caption. And so we hope that the model uses this information to guide the caption generation process, and then we're able to generate meaningful descriptions that can answer the question. So we collect framed captions, and then we give them to the frozen model, and then we ask the model to answer. We give, given all these captions and this question and these options, what is the answer? Okay, that's what we do. And it works surprisingly easy, competitive, and again, it's gradient free. We don't have to tune anything. We don't tweak any parameters. So that's what I just mentioned. The video is decomposed into frames by using uniform sampling. We generate frame captions with InstructBleep. We concatenate all the captions and we give them to the model. Here's an example. Again, it's the same video of the little kid picking up a present. A base captioning template, something that is not question specific, is something like a photo of, we give the frame the photo of, and then the model generates the completion. But a question-dependent captioning template is something like, based on the image, provide a detailed description of the photo. And then for the answering part, the QA prompt is the concatenation of the captions plus the question and the options. Okay? And that's it. Here's an example of the captions that the model generates. A boy is standing near a number of gifts looking for a present to open. He appears excited and interested. So that sounds reasonable. Excited about receiving a gift and wanted to play with it, right? So we give all of this, and then the model is able to answer the question. So we compare Qubit with state-of-the-art models, even a model that was released earlier this year. We compare in gray color. This is accuracy, so higher number is better. These are different benchmarks that we use. Light gray, like it says here, is because we think this, yes, we're going to put them in a table because reviewers are probably going to wonder, but we don't think it's a fair comparison. So we're going to gray you out and say you're using a closed model that we cannot inspect. But even then, our model is very competitive, right? It reaches very similar numbers, and when it falls short, it's not a huge difference with these models or with the models that we have here. Now, like I mentioned, these are 4 different benchmark data sets for video question answering. You have different performances here, varying from 41, from the 40s to the 70s. The differences in performance have to do with the fact that these data sets are very different in nature with respect to the type of questions. Like some of them are very reasoning intensive, like the one of the paintbrush, right? You have to reason about why you do that. Why are you using the water when you're painting? We know that because we have a lot of common sense. We have done it when we were kids. And then some other benchmarks, for example, have a lot of questions like the one I showed you with the backpack, but they ask you, like, can you list the objects in reverse order in which they were placed in the backpack? That's really hard. And so that's why you see different performances. But overall, we're very happy to see that we can stay within closed models, within reasonable GPU budgets, and have competitive results. These are ablation studies on the type of captioning prompt. So this is when you have general captioning prompts, like a photo of X, and this is where you have question-dependent prompts. And we're comparing the XL versus the XXL pre-trained language model. So this is the Flantify model, the XL size, and the XXL size. So yeah, larger model will do better, right? And in general, question-dependent are doing a little bit better than generic captions. And so it seems to indicate that it is important that you guide your caption generation with the question you try to answer. It just makes a lot of sense for us, right, from our point of view. And that's it. So visual question answering is still very much an open problem. Numbers are very slow, so it means that there's a lot of way to go in this problem. Current models struggle with temporal reasoning, so some of our preliminary experiments and doing analysis, we find that these models are not very good at reasoning about sequences of events or predicting what is happening next. So like if I open my hand here, like everyone will know that this thing will fall into the ground, right? And as humans, we learn that very quickly from a young age, that if you don't grab something, gravity will happen and the things will drop. But the models cannot predict that. So if you ask one of these models, what will be the next image after I do this, they will not predict the trajectory of the object. So these kinds of things, and for example, the other understanding what is the sequence of events, that is also very hard for the models to do. The information from the video is pretty hard to interpret and to extract. I think we still have a lot more to do with respect to getting more semantically coherent representations of the videos. But we also learned that instruction-trained models like instruct bleep are better for these type of tasks. And like I mentioned, evaluating closed models as part of the solution is not the best approach to make progress. We cannot inspect them. We cannot understand what is happening. And so that's not reproducible. And we need a lot more work for long videos. So thank you so much for your attention. This is work that I've done with research assistant David Romero. And hopefully you liked what I talked about today. Happy to take questions.
We have some time for questions, if you don't mind. Actually, I have one question. I'm used to working with textual Q&A. In textual Q&A, it's a bit different, the context, because usually you start with lots of documents, and you ask, I don't know, there are many documents about the ocean, and then you ask something about the ocean. But here, it seems to me like it's always a question about one video.
Yeah.
Do you work with? Is there work with like many videos, and then you ask, well, is there a boy getting a gift? Where's that video? Is this something you do or something that people do?
And so the closely related thing that I think about that is multimodal information retrieval, not necessarily question answering, but like if you can do across modalities. You do a search. You express a query in either visual, language, or audio modality, and then the model has to answer based on a collection of videos or text or audio clips. But for this, I'm not aware. Like I personally think that the problem is so complex that we first start with the simplest thing, like this is where you will get your answer, right? Not in the general question answering is like an open-ended or closed collection of documents, and here is like, this is this image, I want you to answer this question about this. I believe that as we make progress, that we can get more to an open-ended task, but I'm not sure if these other models that I mentioned work in an open setting. Benchmarks are not, right? Benchmarks are video specific.
Questions?
I'm a bit curious about how do you evaluate those models. I think you showed some examples where they were like multiple choice questions. So it's the question is about how do you evaluate the models? Like you were showing those numbers, but what do they actually capture? Is just like some kind of blue score or?
It's accuracy. I'm sorry, I should have mentioned. It's accuracy. Most of these are multiple choice question answering, which means that you have 3 or 4 possible options, and you compare what the model says with your gold standard. Some of them can be just a question, and you compared if the right. No, all of this is accuracy, so it's multiple choice for all of this.
And do you think the performance would keep about the same if it were not multiple choice, if it were like having to produce text? Like if you use the model, does it make sensible text when you use the model in a free form?
Yeah, you can use them, but it's much harder. One of the options that you can do is you can do control generation or constraint generation, where you allow the model only to choose text that is part of that is related to some of the answers, or you can do. So the problem is that if you leave it open-ended and you just generate language, the evaluation is very complicated, because during decoding, like the model can generate anything, any strings or any words that are semantically equivalent, and then the evaluation becomes a nightmare. So the best thing, the easiest thing that we're doing is this one, right? Because you just give an option, and you can compare letter with letter, basically.
Right. And then in those cases are like 5 alternatives. So
some of them have 3, some of them have 4. So it's it's an artificial setting, right? It's a much easier task. Like we as humans don't need the options. We can just watch the video and answer the question without needing the options, right? But we try to make it easier for models.
I have a sort of a selfish question. So I want to understand your computing facility. I mean, you said that you have a supercomputer available.
Yeah.
And we're discussing our infrastructure here. So we're discussing whether we should have more cloud computing or some central facility. What do you have exactly?
Yeah.
What is the supercomputer? Do you actually use it? Do you need to use the cloud most of the time or not? Or how is it in your institution?
So at University of Houston, I have my own GPUs. So my group has access to my own GPUs. They're not the biggest, but so far they have sustained the research efforts of my group. At MBZ, the university has a very large cluster of physical GPUs on site. But however, those resources, these are very high end and it's a large number of them, but they are assigned to work that is doing large language model research. And so researchers that are attached to those projects get access to these super fancy high-end computers. People like me that are not doing, I don't really care much about research on language models, honestly. I care more about what can we do aside of that, building the next large language model. And so I don't have access to those. Our department in specific is trying to resolve our compute needs by using the cloud. So right now we bought a lot of Amazon credits for this coming year, and that's how we expect to provide resources for our research groups this year. And then in the future, we are in a special kind of situation also because of the political environment, and like the US is forbidding US people to sell GPUs to us because they think we're going to sell them to other people. They don't want them to have access to GPUs. So the whole thing is like complicated with GPUs. And so I'm not sure how that's going to resolve. But in the meantime, we do get access to the cloud. And so it's just a matter of figuring out the right setup. For the type of experiments that we need to do, using Amazon, the cloud infrastructure needs to have the right setup for us to work with. And right now we're trying to figure that out.
So I actually had the feeling that to run these models, you needed a large cluster, but perhaps not.
No, you don't need. No, these experiments are run on. We have access to a 4-node GPU cluster to run some of these experiments. So it doesn't have to be super large. That's why we're not doing experiments with the Sevilla model. Sevilla requires a lot more, particular GPUs with larger memory. We don't have access to those. Maybe the large language group has access to those.
Okay, well, it's similar. Similar to what we have. We have a cluster.
Yes.
Any other questions to close? Maybe a short question.
Okay, hi. Thank you for your presentation. Can you explain more about how the sampling of the frames? Because I assume the videos have different lengths, so you use different numbers of frames for each video. And in addition, I understand that you give the temporal information by just putting the captions in order. Do you also use some timestamp to tell the difference between the frame?
No. Yeah, good questions. So for the first question, all the videos, we did preliminary experiments where we took different numbers of frames. I used to have the slides, but I deleted them. We ended up keeping 64 frames per video. And these are short videos. These are 1 minute, 1 minute and a half clips. We don't have super long videos like the lobby model. But the results were better with 64 frames per video. Okay. And the second question was time step. We don't give to the model. I think that's something that could be improved during pre-training or during the representation itself. We just give it as a sequence of sentences. Mm-hmm.
All right, so we have a couple of minutes. So there's actually a question by the people watching in the internet. It's a question, there you have it. It's a question about the physics understanding of these models and action modeling, which is tough thing. Maybe you have some words and thoughts about this.
Yeah, definitely. There's a lot of lack of understanding of the physical world in this kind of I'm sorry, excuse me. in these type of models. And we could do much better than that. Some things that you can do, for example, simple things could be like during pre-training. During pre-training stage, you may be able to train the model to put the frames in order, for example. That's one of the things that we have discussed. Like if you give the unscrambled set of frames and you ask the model, give me the correct order, or you give a sequence similar to what we do in language models, and you give a sequence of frames and you say, predict the next one. Same as what we predict in the next word. It's not clear that a robust understanding of the physical world will come out of doing these things. But it's definitely something pointing towards our problem, right? Some people claim that we should not be doing the transformers, and attention may not solve all our problems, right? Because of how complicated it is to extract this useful knowledge. But right now, these are things that we can do. That's a very good question, and I'm not sure what is the right way to solve that lack of understanding. Yeah.
Okay, I guess that's it. Thanks a lot for coming by, and thanks a lot, Thamar, for the excellent talk. Thanks a lot.
Thank you for having us. Happy to be here.
Obrigado.
Obrigada. Muito